Alrighty, hello world. Today we're going to do some implicit differentiation with multivariable functions. This is pretty important to know because if you get an implicit function, it can really ruin your day. So the first part is to understand what an implicit function actually is, so you know when to use this. That's pretty easy. An explicit function, it's like you get y equals x to the fourth plus cosine x. You can see there, like, you can manipulate that anything you want. You can get x on one side, you can figure out y. It's nice, and you can derive nice and easy. Implicit is where you have something like this, sine of xy. You can't really move that around. You can't really get all x or all y onto one side. I mean, you probably could, just looking at it, you probably could if you use sine inverse here, but it would be really ugly, and it'd be a big waste of time. So that's what explicit and implicit is, and the question is, when you get implicit, how are you going to derive? And that's where implicit differentiation comes in. So, scroll down here. I wrote down an example here. Given x squared plus y squared plus z squared equals sine of yz, find dz with respect to x. Alright, now this isn't that bad at all. What you're going to do is, since you're deriving with respect to x, you're going to treat all the x's as you normally would. You're going to derive them normally. Like x squared, see that? It's on its own. It's going to become 2x. That's no problem at all. Now when you come across the y's, you're going to treat them, see, it's not here at all. You're going to treat them like a constant. If they're attached to a variable, they hang out. They come along for the ride. If not, derivative of a constant is always 0. So in this case, y is not touching anything here. So 2x plus 0. Now when you get to z, what you're going to do is, see how it's on top? You're going to derive it like you normally would if you were deriving with respect to z. But you're going to tag onto it a dz dx. Let me show you what I mean. So it's going to be plus z squared, so it's 2z, kind of like it normally would, and then dz dx. I'll show you what we're going to do with that in just a second. So now we got the other side to do, equals, alright, derivative of sine is cosine. And keep that yz in there. And now we got to chain rule it out. Y is a constant, so it's just coming along for the ride. So it's going to be 1 times dz dx. Alrighty. Now, this gets you this big ugly thing, and I know what you're probably thinking, Mike, how the hell do I find dz dx? This is not a suitable answer. Well, what's nice is, if you look at it, you have dz dx actually defined in the function. You can actually bring them all over to one side. So, what you're going to do is you can move it around. Let's see how we're going to do that. Got it. Oh, my roommate Josie's here. Josie, say hi.
Oh, hi.
Yep, I'm just teaching the world how to do this. So, I'm going to pull it all to one side, because we can do that. 2x plus 2z dz dx minus cosine yz times dz dx equals 0. Alright, so we're going to factor the dz dx out of these two and pull that over there. We're going to do that at the same time. So we're going to get dz over dx. That's Jersey doing dishes in the background. dz over dx times 2z minus cosine of yz equals negative 2x. Alrighty, now we're pretty much ready to just finish this up. dz over dx equals negative 2x over the quantity 2z minus cosine of yz. And there you have it. And that is implicit differentiation. It's just a pretty basic example for you. Can't really think of any situations that wouldn't cover. All the derivative rules still apply, product rule, look out for chain rule. And yeah, just get good with manipulating the algebra. And that's that. So, yeah, that's all I gotta say. Yeah, I'm filming.
Jersey, do you have any sense of courtesy at all?
Alrighty. I will see you later, team. Mike out.